Hey everyone, it's Zach. Last episode we traced 70 years of AI history in one straight line. Today we're going deep, focusing on the most important technology in that story, deep learning. Why did a brain-inspired computational model change the world? Let's find out together. AI Basics, Episode 2, let's go. Today's theme is deep learning and neural networks. I'll explain why deep learning rewrote AI history using 3 angles. First, what a neuron actually is. Second, why stacking layers makes a network more powerful. And third, what fundamental limits deep learning still has. By the end of today, the words neural network won't be a black box for you anymore. March 2016, Seoul, South Korea. Lee Sedol, ranked as the world's best Go player, lost 4 out of 5 games against Google's AI, AlphaGo. Go has more possible board positions than there are atoms in the observable universe. Experts said computers couldn't beat humans for at least 100 more years. The technology that made that upset possible was deep learning. How did a neural network surpass the greatest human intelligence in one of our most complex games? That's the mystery we're solving today. The foundation of deep learning is the neuron. The human brain contains roughly 86 billion neurons, nerve cells connected to each other through electrical signals. An artificial neuron is a mathematical model of this. It takes multiple inputs, multiplies each by a weight, adds them together, and if the sum crosses a threshold, it fires, sending a signal forward. That might sound complex, but the idea is simple, a small unit that combines many inputs and decides whether something matters. The history of artificial neurons starts in 1958. Frank Rosenblatt invented the Perceptron, a single artificial neuron that could solve linearly separable problems, like distinguishing spam from real email. But in 1969, Marvin Minsky proved that the Perceptron couldn't solve the XOR problem, and AI funding collapsed. The first AI winter arrived. But researchers who refused to give up would find a dramatic solution decades later. The XOR problem: if both inputs are the same, output 0, otherwise, output 1. You cannot separate these cases with a single straight line. But with 2 or more layers, a multi-layer network, you can. The first layer creates an intermediate representation that transforms the problem, and the second layer solves it from there. The lesson: stacking layers lets you represent increasingly complex patterns. That idea became the core of deep learning. Multi-layer networks could theoretically solve XOR, but between 1969 and 1986 there was a fundamental unsolved problem: how do you efficiently adjust the weights in every layer? In 1986, Rumelhart and Hinton made backpropagation practical. The idea: take the error between the prediction and the correct answer, and propagate it backwards from the output layer to the input layer, nudging every weight a tiny bit. That made it possible to train networks with millions of parameters simultaneously. 2012 was the turning point for deep learning. In the ImageNet image recognition contest ILSVRC, Geoffrey Hinton's team at the University of Toronto used a deep convolutional neural network called AlexNet and slashed the error rate dramatically. The gap over second place was enormous. While other teams had been improving incrementally, AlexNet made a giant leap. The entire research world shifted to deep learning overnight. That's why 2012 is called the birth year of deep learning. Let's look inside the CNN that revolutionized image recognition. The first layer detects edges, vertical and horizontal lines. The next layer combines edges into corners and curves. Deeper layers pick up partial features like eyes and ears. The final layer makes the call: this is a cat. This hierarchical feature extraction closely mirrors how the human visual cortex processes images. The remarkable part: AI learns all of these feature detection filters automatically, from data alone. Why does adding more layers make the network more powerful? The answer is layers of abstraction. A shallow network can only capture features close to the raw data. A deep network learns step by step, from low-level edges to high-level concepts like dog or car. If you tried to match the same representational power with a shallow network, you'd need an exponentially larger number of neurons. Depth lets you represent complex patterns efficiently with far fewer parameters. That's the core advantage of deep learning. If CNNs excel at images, recurrent neural networks, RNNs, are designed for sequences and text. An RNN feeds its previous output back as the next input, letting it maintain context over time. But standard RNNs had a problem. With long sequences, they forgot earlier information, the vanishing gradient problem. LSTMs, introduced in 1997, solved this by learning what to remember and what to forget, enabling major advances in speech recognition and machine translation. This is the important setup for the transformer we'll cover next episode. Deep learning is powerful, but it has real limits. First, data dependence. It needs massive amounts of labeled data to learn. A human child can recognize a dog from a few photos, AI needs tens of thousands. Second, the black box problem. We can't explain why the model made a particular decision, which is a serious issue in medicine and law where accountability matters. And third, distribution shift. When the model encounters inputs that look different from its training data, performance can drop sharply. These are the core research challenges for the next generation of AI. Let's go back to where we started. Why could AlphaGo beat the world's best Go player? Because deep learning let it study tens of millions of game records and find patterns no human had ever seen. Here's the summary. An artificial neuron is a simple unit that weights its inputs and decides. Stacking layers enables step-by-step learning of increasingly abstract features. Backpropagation in 1986 and ImageNet 2012 were the historical turning points. CNNs excel at images, LSTMs handle sequences. And the fundamental limits, data dependence, black boxes, and distribution shift, are still open problems. Today we covered the LSTM. Next episode, we're looking at the model that made it obsolete, the transformer. Why can ChatGPT speak Japanese, English, French, and dozens of other languages fluently? The answer is in one paper published in 2017. Once you understand how it works, the way you see generative AI will completely change, I promise. Subscribe so you don't miss it. See you next time. Don't miss the next episode. Subscribe to the channel and hit the bell.